starting a new chapter now. Just finished the ionic compounds. And we're going to go into the second of the two chemical bonds that we are going to deal with, and that these are covalent bonds in the last chapter, ionic bonds. Just a little reminder, there's a third type of bond called the metallic bond, which we are not going to discuss. It doesn't really develop compounds, it just shares electrons amongst many atoms of metals in the same semi-plane, which explains why they're really good conductors of electricity. That's not what we are into. We're into the compounds, how they're created, why they're created, and what we can do with them later on in the chapters. So the ionic compounds, just to refresh your memories, where atoms took electrons or gave up, what they call accepting and donating electrons. If they accepted electrons, they became negative because now they had more electrons than protons. If they gave up electrons, that made them positive because now they had more protons than they had electrons. The similarity between the two is that they are both driven by the same rule, the Octet Rule. The Octet Rule basically said that all atoms want to act like they're noble gases. And that means they end up with 2 s's and 6 p's or 8 valence electrons, hence octet. Covalent bonds, when you do this completely different. Instead of donating and accepting, it's going to be sharing. You're going to share electrons to get to this nirvana, if you will, for chemicals. So, let's take a look how this works. Oh yeah, to show you the outline, I'm just stripping the outline. I'm not going to go through this too literally. I'm going to do a lot of the work on the smart board, so the PDF form would be the best form to look at for this. But this is the general outline that we're going to follow. We're going to learn about the Lewis-Dot structure. We're going to learn about the 3 types of covalent bonds, single bonds, double bonds, and triple bonds. So that's our tack today. Probably take 2 videos to go through this. Alright, so let's start off with the Lewis-Dot structure. Now the Lewis-Dot structure was developed by a scientist named Lewis, oddly enough. And he devised the whole idea of making sure that everything ends up with 8 electrons, with the exception of hydrogen, which only needs 2 electrons. So we're going to start off with just the same element that creates molecules within themselves. We'll start off with chlorine. Now, when Lewis developed the system of showing electrons in the outermost level, the valence level, he used the symbol as the nucleus, if you will, in which the electrons would be scattered around. And he went 1 electron at a time. So if you take a look at chlorine on your periodic chart, it's in group 7A. Now, as I told many of you, that the A column of these elements tells you how many valence electrons there are. So since it's in 7A, it's going to have 7 valence electrons. So 1, 2, 3, 4. Start off putting them in a north, south, east, west direction. And then we start pairing them after that. North, east, or northwest, and south. And that's going to be this one lone unshared pair of electrons here. Unshared electron, not pair. Unshared electron, no pairs. These are pairs here. This is not a pair here. Do the same thing here, north, south, east, west, or north, east, and south there. And so we have these 2 singular electrons opposite each other. Now you can see here, we have 7 electrons in each of these chlorines. If we did what we did last chapter, we take this electron here, move it over here, and now chlorine is happy with the 8, but this chlorine is not happy because it only has 6. That's not going to work. But generally you find that covalent compounds are all nonmetals. not generally, always, you'll find all nonmetals. You'll never see a metal in a covalent compound. And that becomes rather important later on when you start identifying phases of compounds. But for right now, the only way that this is going to happen is if this electron is shared over here, this has 8, this has 6, that's not going to work either. But if they allow the electrons to go back and forth between the two atoms, in what we call a hybrid molecular bond, this is a thing. This happens. So if we draw this right here, this is what we call a circular Lewis dot structure. Now the official Lewis dot structure uses lines and not circles. But this is like our rough graph right here. So the circular Lewis dot structure form gets us to the final form, which is the line or the linear Lewis dot structure. And the line represents the fact that we are sharing a pair of electrons right here. So we rewrite it like this. And then we have to include all unshared pairs of electrons around it, knowing that this represents 2 electrons right here. Okay? We call this a single bond. And if we look at each individual chlorine, we have 2, 4, 6, 8, 2, 4, 6, 8. The octet rule is satisfied. So this is a thing. Hydrogen does kind of the same thing. But hydrogen is in group 1A and only has 1 electron. And so put the 1 electron facing each other. And because hydrogen's in the first level, how many electrons does it take to be full? Well, yeah, 2, because the only thing you have in the first level is a sphere. So it's going to share a pair of electrons right here. So this is going to look like this. Now, this is not the octet rule granted because hydrogen doesn't need 8, so we call this the duet correlator. But regardless, same idea. These are very stable structures. In fact, when we find these elements by themselves, they are found in this form. We call these forms diatomic. These 2 atoms per molecule. Now, in this case, it's the same atom, but you have diatomic molecules that are multi, or at least di or bi elements. You can have more than 1 element, you have 2 elements. But the ones that we're going to be describing today are all the same elements. A pair of hydrogens, a pair of chlorines. In fact, you write the formulas of these things as Cl2 and H2. Okay? Okay. Now, that brings us up to oxygen. Oxygen is also diatomic. And the reason for that is because it does the same thing that chlorine and hydrogen do, except a little different. Now, take a look at oxygen. You see that the oxygen is in what A column? If you said 6A, that would be correct. And that 6 of the 6A means there are 6 valence electrons. So north, south, east, west, north, south, east, west. And we want to make sure that we have 2 singular electrons opposite each other and 2 oxygens. So I'm going to pair this one up here, and I'm going to pair this one up here. Now, it doesn't have to do that. It just makes it a little cleaner. Since they both have 6 electrons, they both lack 2 to be full. You can't take 2 off this and go over there, because that gives this one 4. So I'm going to have to share 2 pairs of electrons. Okay? The sharing of the 2 pairs of electrons, now, this is called a double bond. And on your sheet that started before we did the smartboard stuff here, it gives the definition of the double bond as sharing a pair of electrons. But we wanted, this is the circular Lewis dot structure, and we want the linear official Lewis dot structure. And so that's going to look like this. Make the two lines approximately the same. It may show difference where you put the pair of electrons. You want to leave it where you had it there, that's fine. If you like symmetry, you can move these down here, move these down here. As long as you show two distinct pairs of electrons around those oxygen atoms. Again, this is a diatomic molecule. In fact, many people call this atmospheric oxygen. Because the oxygen we find in the atmosphere is all paired up like this. When we breathe in oxygen, it's the pairing of electrons that is going to be undone in our lungs to create the chemical reaction with our hemoglobin, so that the hemoglobin can bond to one of the oxygens and carry it to different parts of our body so that we can exist. Next one is nitrogen. Nitrogen also is diatomic. When you take a look at nitrogen on the periodic chart, you'll see that it is in column 5A. And if it's in column 5A, that means it has 5 valence electrons. North, south, east, west, north, south, east, west. And again, we want one electron facing each other on each nitrogen if we can. And we can. So we pair, excuse me, these electrons here, these electrons here. And that leaves us this one pair of electrons that is not shared yet to be shared between the two atoms. And that is, no, that's not right. I just used 7, didn't I? So let's try that again. Those are the 5 valence electrons. Simply means north, south, east, west, north, south, east, west. One pair of electrons, not 3. I'll try to make it chlorine. Okay, so now I've got 3 sets of electrons here around it. Okay? Now, this is called a triple bond. There's 3 pairs of electrons and each shared between 2. That's a triple bond. And so we represent that over here with 2 nitrogens and 3 parallel lines over here. Parallel to the M. And again, it doesn't make any difference where you put the pair of electrons on, so you have one on one nitrogen, one on the other. You want to leave it where you had it after that's done. Totally understandable, but not necessary. Okay?